Good morning students and welcome to online teaching session. In the previous class I taught Boyle's law wherein pressure and volume were correlated and Charles' law where volume occupied by the gas and the temperature were correlated. Today let us see third law, that is Gay-Lussac's law. What this law says, what is the relationship between the measurable properties of this law and what are the constants? Means any gas to obey Gay-Lussac's law. What measurable quantities should remain constant? And then we will move to one sample numerical. With that, Gay-Lussac's law will be completed, and then Avogadro's law. This law mainly tells the relationship between the volume and the quantity of the gas. Means volume quantity relationship. That will come to know in Avogadro's law. Now let us see first law, that is Gay-Lussac's law. This law states the relationship between pressure and temperature. So we can write pressure, temperature relation. Now let me take one simple example so that the relationship between pressure and temperature can be understood. In the case of automobiles, when the tires are inflated with the air, particularly in this season, sufficient amount of air is pumped into automobiles tires. That air will occupy particular space. Right, that is nothing but volume. And particularly in this season, temperature is low, so slightly more than required amount of air can also be pumped. Right. Next, in summer season, April month, May month, March, in these months, how much gas is required, or gaseous mixture, or air is required to be pumped into automobiles tires? That is slightly less when compared to this season, because in summer season, because of temperature, the air that is pumped into the tires that inflate the tires, but because of high temperature, the air which is pumped into tires is prone to expand. Right, that may lead to bursting of the tire also. So the temperature is more in that season, so the amount of air to be pumped into the tire should be slightly less when compared to winter season. Otherwise, because of the temperature, the volume occupied by the gas or gaseous mixture or air inside the tire increases. That leads to bursting. So that is simple example for Gay-Lussac's law. So here volume occupied by the air inside the tire and the temperature, they are correlated. They are directly proportional to each other. With increase in temperature, with rise in temperature, volume occupied by the gas increases. So these two are measurable properties, and when a particular gas, if you take in this case, the remaining two entities should remain constant. So behavior of the gas can be known on the basis of four entities, four variables: pressure, volume, temperature and amount of gas. Amount of gas means quantity of gas. Quantity of gas is measured in terms of moles of gas. Right? If the number of moles of gas is more, then quantity or amount of gas is said to be more. Right? So here these two are correlated. Means the remaining two things, that is volume and quantity of the gas, should remain constant. So according to Gay-Lussac's law, when the quantity of the gas remains constant and volume occupied by the gas remains constant, then the pressure exerted by that gas over inner wall of the containers is directly proportionate to absolute temperature. This is Gay-Lussac's law. So according to this law, when quantity of the gas, that is small n, and volume occupied by the same gas pressure exerted by it is directly proportionate to absolute temperature. Here absolute temperature means we have to take temperature on Kelvin scale. So this is Gay-Lussac's law, and this can be written in the form of expression like this: P is directly proportionate to T. Here volume and temperature. Volume and quantity of gas, that is number of moles of gas, remain same or remain constant. It's same. Okay. P is equal to, when proportionality mark is removed, we will get a constant, say K into T, where K is equal to a constant. You can say proportionality constant. Okay. Here, if temperature is increasing, when temperature is increased, the gas undergoes expansion. This is the characteristic feature of the gas. As and when we raise the temperature, gas undergoes expansion. As a result, pressure exerted by that gas over inner wall of the container also increases. Right? So, initially, let us say temperature T1. Then, the pressure exerted by that gas is P1. If we increase temperature to T2 from T1, then pressure exerted by the gas will also increase. So, here at T1, pressure exerted by the gas is P1. At T2, pressure exerted by the gas is P2. So according to Gay-Lussac's, if you look at equation number 1, when we take T towards left hand side, P is equal to, P by T is equal to K. Therefore, P1 by T1 is equal to P2 by T2. That is equal to P3 by T3. Again, that in turn is equal to P4 by T4. So that way we can write. So this is an important equation in states of matter. Here we have 4 variables: P1, P2, T1, T2. Out of these 4 variables, if we know any 3, the 4th unknown one can be calculated. So that's about Gay-Lussac's law and the important expression associated with it. So over this, many sample numericals are there. Now let us see the relationship between pressure and temperature in the form of graph. Now what I am going to do is, on x-axis I will take temperature, right, capital T. Capital T means absolute temperature or temperature on Kelvin scale. Next, on y-axis, pressure exerted by the gas I will take. Different values of pressures. And this is in terms of bar. Bar is unit of pressure. Right? And here these two are directly proportionate to each other. So whenever two variables are directly proportionate to each other, we will get straight lines in the graph in this way. When temperature at the beginning, say V1, at temperature V1 means, volume V1, volume is remaining constant. Then when pressure and temperature are correlated, we will get the graph of this type V1. When volume is slightly increased from V1 to V2, then pressure and temperature are correlated, and the straight line will get in the graph in this way. So that way V3, V4, V5, V6 and so on. Here we got these lines V1, V2, V3, V4 when volume occupied by each gas remains constant. So whenever graph is drawn by taking pressure and temperature values on different axes, by maintaining volume of the gas constant, we will get this type of curves, and they are said to be isochores. Isochores. In the case of Boyle's law, you recall, we got isobars. Right? Their pressure and 1 by V, that is reciprocal of volume, were correlated. In the case of Charles' law, their volume and temperature, they were correlated. Right? And they, in the case of Boyle's law, isobar, pressure, temperature. No, pressure and volume, temperature remains constant. There, isotherm, Boyle's law. Therm refers to temperature. And in the case of Gay-Lussac's law, volume is remaining constant. So it is isochores. Isobar, isochores, isotherms. Isobar refers to pressure to be maintained constant. Right, their volume and temperature are correlated. That is Charles' law. In Charles' law we get isobars. bars. In Boyle's law, isotherms. In Gill-Xox's law, isocores. Right? Remember, this part CH mol refers to volume. Here, volume is remaining constant. So that's about Gill-Xox's law. Important expression associated with it and the graph related to Gill-Xox's law. And the one more important concept that is associated with it, that is isochore. This can be asked in MCQs or assertion result type of questions. Now, let us see one sample numerical that shows the relationship between pressure and temperature. In a closed container, ideal gases initially have a temperature of 27 degrees centigrade. If the final pressure becomes twice the initial temperature, what is the final temperature? So here initial temperature is 27 degrees centigrade. Initial temperature means T1. It is 27 degrees centigrade. As I told you earlier, temperature should be always expressed in terms of Kelvin. That is on Kelvin scale. So we need to add 273.15 or 273. Right, this is equal to 300 Kelvin. So this is T1, initial temperature. Right, next. Final temperature, that is T2. We don't know, we are asked to calculate. So let this be question mark. Next, ideal gases initially have this temperature. If the final pressure becomes twice the initial pressure, so initial pressure means pressure at T1. So P1 is equal to P. Final pressure if the final pressure becomes twice the initial pressure. So initial pressure is P. So final pressure P2 will become 2 times to that of P, that is P plus P, 2P. Right? So here we have two temperatures T1, T2 and pressure values 2, that is P1, P2. So when this data is correlated, according to Gill-Xox's law, we will get that is P1 by T1 is equal to P2 by T2. Accordingly, if we substitute, so P1 is P by T1 300 Kelvin equal to P2. P2 is double to that of P1, so 2P we write by T2. T2 we don't know, we need to calculate it. So T2 is equal to 600 Kelvin. We will take T2 towards left hand side. Right, multiplication and division are involved in this. So that's about this sample numerical. So remember one thing, temperature should be always on Kelvin scale. If it is given on Celsius scale, by adding 273 or 273.15, we can convert it to Kelvin. So that's about the sample numerical on Gill-Xox's law. Now let us see Avogadro's law. Before moving to Avogadro's law, let me explain the terms ideal gases and real gases. Ideal gases are those gases which obeys gas laws. Boyle's law, Charles' law, Avogadro's law. This law now we are going to discuss. And those gases which deviate from ideal behavior, means those do not obey Boyle's law, Charles' law and Avogadro's law, they are known as real gases. Next, one more thing, that is STP. After this, I will move to Avogadro's law. STP refers to standard temperature. This is always equal to 273.15. Standard pressure, it is always equal to 1 bar. Right? Bar is unit of pressure. Atmosphere is also unit of pressure. 1 atmosphere is equal to 1.03 bar. That is the relationship between both the units of pressure. That is atmosphere and per bar. Atmosphere itself is unit. And temperature over, pressure over, and then volume. Any gas, if its quantity is equal to 1 mole, 1 mole of any gas at STP occupies 22.7 liters. So these are the important things which you need to remember. This will be helpful while working out the numericals. So volume occupied by 1 mole of gas is called molar volume. Okay, fine. Now let us see Avogadro's law. Boyle's law, pressure and reciprocal of volume were related. Gill-Xox's law, pressure and temperature were related. And in the case of Avogadro's law, volume and quantity of gas, that is number of moles of gas, are correlated. So in this law, volume and quantity of gas are correlated with each other. Okay. As we know the measurable properties, pressure, volume, temperature and number of moles of gas. These will decide the behavior of the gas. And in the case of Avogadro's law, as it is written, volume and quantity of the gas are correlated. Means volume occupied by any gas is directly proportionate to number of moles of that gas or quantity of the gas. Next, gases are made up of molecules. So quantity of gas is directly proportionate to number of molecules present in it. More the quantity of the gas, more the number of moles of the gas, more will be the number of molecules present in it. Therefore, here we can say volume and quantity of the gas are correlated with each other, or volume and number of molecules are correlated with each other at constant temperature and pressure. So we can write it this way: at constant temperature. Again, here we need to take capital T only, that is absolute temperature. And pressure volume occupied by the gas is directly proportionate to quantity, means number of moles. Of the gas. As I told you, quantity of the gas refers to number of moles of gas. Mole means particular quantity of the gas containing 6.022 into 10 raised to 23 number of molecules, and this number is known as Avogadro number. So 1 mole of any gas will have Avogadro number of molecules in it. So here volume and quantity of the gas, or volume and number of moles of the gas, can be correlated in this way. V is directly proportionate to M. As I told you, N stands for number of moles of gas, right? So 1 mole of any gas will have Avogadro number of molecules. So we can say here volume occupied by the gas is directly proportionate to number of molecules of the gas. Conditions: temperature and pressure remain constant. So here, when proportionality mark is removed, we will get a constant that can be called as proportionality constant. Let this be equation number 1, where V is equal to volume occupied by the gas M number of moles of gas means quantity of gas, or we can write number of molecules of gas. Right. When this proportionality mark is taken towards right hand side, or when small n, that is quantity of the gas, is taken towards right hand side, we will get constant, that is V by N is equal to K, that is nothing but a constant. So one thing, here I have written quantity of the gas, in its place we can write number of moles of gas, or we can write number of molecules of the gas. So I will define again this in a different way, slightly keeping the molecules in the mind in place of quantity of the gas or number of moles of the gas. That is, when temperature and pressure remains constant, volume occupied by any gas is directly proportionate to number of molecules present in that gas. That's about Avogadro's law. And here, small n stands for number of moles of gas, which is equal to mass of the gas divided by molar mass of the gas. Small n stands for mass of the gas, and capital N stands for molar mass of the gas. And here, if you take this as second equation, and when this is substituted in equation number 1, we will get V is equal to Km divided by capital M. And in this expression, Right? Let this be equation number 2. When equation number 2 is substituted in equation number 1, we got a new expression, that is equation number 3. And in this, K is constant. And molar mass of the gas, that also remains constant. Right? If you take a particular gas, 1 mole of gas will have particular mass, that is called molar mass, that is constant for that gas. So here K and M are constants, and V and small m are variables. Out of these two, if we know any one, the other one can be calculated. Number 2, if the name of the gas is not mentioned specifically, then the variables will be 3. Volume, number 1, mass of the gas, small m, number 2, molar mass of the gas, that is capital M, number 3. K is constant. So when the name of the gas is not mentioned particularly, variables will be 3, V, small m and capital M. In that case, out of those 3 variables, if any 2 are known, the third unknown variable can be calculated. So that's about Avogadro's law and the important expressions involved. Thank you, children. Good evening, children. In continuation with the chapter States of Matter, now let us see the important topic, that is ideal gas equation or combined gas equation. So today's topic is ideal gas equation. I'll teach ideal gas equation. It's about the derivation and the information given by the ideal gas equation and its importance. That is one point. Thereafter, I will move to one sample numerical. So, ideal gas equation and one sample numerical. That is what now I am going to teach. First, let us see ideal gas equation or combined gas equation. This equation can be obtained when the gas laws like Boyle's law, Avogadro's law and Charles' law, when all these 3 laws are combined, then we will get ideal gas equation. Now let us see how they are combined and how we are going to get combined gas equation. According to Boyle's law, V is inversely proportionate to P, or P is inversely proportionate to V. This is not to us, right? And according to Charles' law, V is directly proportionate to T. Volume occupied by any gas is directly proportionate to absolute temperature. And then the third law, that is Avogadro's law. According to Avogadro's law, V proportionate to N. These are the 3 laws. These laws speaks about behavior of the gases. Okay. When equation 1, 2 and 3 are combined, we will get combined gas equation, that is V proportionate to NT and inversely proportionate to pressure. So when equation 1, 2 and 3 are combined, we get V proportionate to NT by P. Or this equation can be rearranged in this way. When P is taken towards left hand side, PV is equal to nRT. This is important equation. Actually, we will get here PV is directly proportionate to NT, and when that proportionality mark is removed, PV is directly proportionate to NT. When that proportionality mark is removed, we will get PV is equal to nRT. This is important equation, ideal gas equation, because this is obtained when Boyle's law, Charles' law and Avogadro's law are combined. And in this equation, R is equal to universal gas constant. And about P, V, N and T are known to you, because when I started Boyle's law, then I explained what do this PV stand for. In Charles' law, VT, so also in Avogadro's law, V and N. Once again, in short, let us see ideal gas equation. This is obtained when Boyle's, Charles and Avogadro's laws are combined. According to Boyle's law, volume occupied by any gas is inversely proportionate to the pressure exerted by that gas when quantity of the gas, small n, and temperature on absolute scale remains constant. Next, when we move to Charles' law. According to Charles' law, volume occupied by the gas is directly proportionate to absolute temperature at constant pressure, and the quantity of the gas when remains constant. Quantity of the gas here refers to number of moles of the gas. Right? So 1 mole of any gas occupies specific volume at STP, that is 22.7 liters. Okay, next is Avogadro's law, third law. According to this law, when pressure and temperature remains constant, then volume occupied by the gas is directly proportionate to quantity of the gas. Here small n stands for quantity of the gas or number of moles of gas. Number of moles of any gas indicates presence of Avogadro number of molecules in it. And those many molecules will occupy a specific volume called molar volume, which is equal to 22.7 liters at STP. STP stands for standard temperature and pressure. Here standard temperature is 273.15 Kelvin and pressure is 1 atm or 1 bar, depending on the data given in the numerical. We will go for the particular unit of the pressure. So here what we are doing is we are unifying, we are clubbing these three laws. The common thing in all these three laws is volume. So volume is indirectly proportionate to pressure or directly proportionate to temperature or directly proportionate to quantity of gas, depending on the law. So when these three laws are combined, we will get V is directly proportionate to product of quantity of gas and temperature on absolute scale, and inversely proportionate to pressure. When P is taken towards left hand side, we will get PV is directly proportionate to NT. When this proportionality mark is removed, we will get a constant, that is capital R. So PV is equal to nRT, where R stands for universal gas constant. So that's about small derivation of ideal gas equation. So those gases which obey PV is equal to nRT is said to be ideal gas, and the gas which deviates from this law is said to be the real gas or the not ideal gas. And here in this derivation, if we take T towards left hand side, we will get PV by T is equal to NR, where NR both remains constant, right? If we change the temperature, imagine initially temperature is T1, right? And we increase that temperature. So at the temperature T1, pressure is equal to P1, volume is equal to V1. If we increase temperature from T1, say to T2, then pressure will also be changed and that will be P2 and volume will be V2. That will be equal to again NR. NR nothing but constants. So we can write in general P1 V1 by T1 is equal to P2 V2 by T2. In this equation, we have 6 variables. Out of these 6 variables, if we know any 5 variables, the 6th unknown variable can be calculated. Or in PV is equal to nRT. R is constant. Right. So variables will be 4. Pressure, volume, quantity of the gas and temperature on absolute scale. Out of these 4 variables, if we know any 3 variables, the 4th unknown variable can be calculated. So now let us see one sample numerical on ideal gas equation, that is P1 V1 by T1 is equal to P2 V2 by T2. Now let us see its solution. Imagine if this type of numerical is given for 2 marks, how those 2 marks are divided. First you will write the data given in the numerical which carries half mark. Formula required, that you will recall by correlating the data, half mark. Next you will substitute the values, half mark, and then you will go for cancellation. You will get the result with appropriate unit that carries half mark. So 4 half marks equal to 2 marks. That is marking scheme. Now let us see the data given in this equation. A gas has a volume of 800 ml at minus 27 degree centigrade. So here volume, that initial volume of the gas is 800 ml. Initial volume V1 is equal to 800 ml and initial temperature that is T1 is equal to minus 23 degrees centigrade. Here capital T stands for absolute temperature, therefore we need to add 273. So when we add 273 to this, it will become 250 Kelvin, minus 23 degrees centigrade plus 273. Next, final 23 and 300 torr, initial pressure. P1 is equal to 600 torr. Torr is unit of pressure. Right, 1 torr of pressure is equal to 1 by 760 millimeters of mercury. Okay, next is what would be the volume of the gas at 227 degrees centigrade and 600 torr. So final temperature that is T2 is equal to 227 degrees centigrade. Again, this should be expressed on Kelvin scale, so we'll have plus 273. 3, 7, 10, 7, 2, 9, 1, 10, 2 to 4, 1, 5. 500 Kelvin. Next, final pressure. P2 is equal to 600 torque. Final volume, that is V2 is equal to question mark. That we need to find out. This data carries half mark. So just you need to go through the numerical and you need to write the data. Just copying the data from the numerical, that's all. This carries half mark out of 2. Next, when we correlate this data, we will get the equation in the mind, or formula in the mind, that is T1 V1 by T1 is equal to P2 V2 by T2. This is the formula, where we need to calculate V2, that is final volume. So V2 is equal to P1 V1 by T1 into T2 by P2. Now if we substitute the values, P1 is 600 torque into V1 800 ml divided by T1 minus 23 degrees centigrade, that is equal to 250 Kelvin, multiplied by T2 is 500 Kelvin divided by P2. P2 is 600 torque. P1 600 torque. Yeah. Now 600 gets cancelled, 250 2 joule. So this is equal to 1600 ml. That is the final volume. So that's how you need to work out the numerical. Here volume V2 is not known to us. So out of these 6 variables, any one can be unknown. That can be calculated in this way. So that's how the numerical is solved. This is one sample numerical. There are many numericals in NCERT exercises based on this formula.